Next, we want to look at charging RC circuits. An RC circuit is a circuit that has a resistor and a capacitor connected in series with a battery. So here we have a battery that has a positive terminal here and a negative terminal there, and a voltage represented by the symbol E, which you might recall stands for EMF. Those V and E are used pretty interchangeably when you're talking about batteries. It's just the voltage, so it's the voltage in the battery. And then, of course, we have a switch here, a capacitor, and a resistor. And what we want to look at is what happens when you close the switch and allow the capacitor to charge. Now we know from the Kirchhoff loop rule that if I go around any closed loop in a circuit, the sum of the voltage drops and voltage gains must be equal to 0. So this is what I have here. I've got the sum of the voltages. As the current goes through the battery, there's going to be a voltage gain, and then when the current goes across the capacitor, there's going to be a voltage drop of Q over C. That comes straight from our equation that Q is equal to VC. So if I solve for V, I get Q over C, and that's the voltage drop across the capacitor. We also know that as the current goes through the resistor, that there's going to be a voltage drop V equals to IR, or that's just simply Ohm's law. So that gives us all the voltages in the circuit. We have the EMF, we have the voltage drop across the resistor, and we have the voltage drop across the capacitor, and the sum of all those voltages has to be equal to 0. That's basically just conservation of energy. Now, there's also a notation here. We have a Q here, and we have an I there. But those two things are related because the definition of current is that I is equal to the derivative of the charge with respect to time. So current is dq over dt. And I can plug that in for I, and that gives me an equation that has only Q as my variable. So that gives me that E minus dq dt minus Q over C is equal to 0. And I've simply plugged in, and there should be an R there. I've simply plugged in I is equal to dq dt there, and that's that equation. And I can solve for E, and we see that right there. Now, this is a first-order linear differential equation. We know that it is first order because it involves a first derivative, and so there's a dq dt term and there's a q term. And we saw last semester that we can solve this kind of equation using the separation of variables technique. We use that when we derive the kinematics equations and a couple of other places last semester, but go back and look at how we derive the kinematics equations for more detail on this process. But I'm just going to show you how it works real quick here. So I've got this 1 over c here. I'm going to multiply every term by c to get q by itself. And so I multiply through, I get a CE, I get RC, and then I get c over c canceling and leaving me with just a q there. And what I want to do is I want to get all the q terms by themselves and all the other terms by themselves. I'm separating the variables. And so I've got this term. If I divide both sides by this term, it'll come out underneath the dq, and I'll end up with dq over CE minus q. And then the RC and the dt, they combine. So if I bring this dt up here, I get dt over RC, and I have separated those variables. From there, it's pretty straightforward. We're going to do an integral on each of those. And of course, the q integral is going from some 0 to some q, and the t integral is going from some 0 to some time t. Now this t integral is pretty straightforward. The integral of the constant's going to come outside the integral, and the integral of dt is just t. This integral is a little bit more tricky. We've got a dq over q, and so you might recognize that as a natural logarithm, and it'll be the natural log of this argument, but because of the chain rule, we're going to have this minus q, so there'll be a minus sign coming out. Okay, so we have this term here, this dq over ce minus q, and we've already said that that's going to be negative the natural log of this argument ce minus q. And the limits, when we plug in the limits, q equals to 0 and q equals to q, and we'll get this when we take those limits in. So I've got minus ln of ce minus q minus ln of ce. That's the one where q is equal to 0, so that term goes away. And that is, of course, equal to the integral of the right-hand side, which is simply t divided by the resistance times the capacitance, RC. After rearranging this with a little bit of algebra, if you distribute this minus sign, it'll become positive, and you'll have this guy is negative, that guy is positive, that guy's positive. If you multiply everything by a negative sign, that lets you rearrange this more simply, and I get ln of ce minus q minus ln of ce equals minus t over rc. You can see the minus sign up here has been, there's a minus sign here. There was not one up there, but we've basically multiplied everything by a negative to arrange this and put it in a nice form. So, if we combine these two logarithms, you know the difference of two logarithms you can write as a logarithm of the fraction, and this term ce minus q over ce, this next step is a little bit tricky. ce divided by ce is simply 1, and qe divided by ce is qe over ce. So essentially what we've done here is we've done the common denominator backwards. So we went from having a common denominator to separating it out into individual fractions, where this is 1 over 1 minus q over ce. And of course, that is in the argument of the natural logarithm equal to minus t over rc. To solve for q, we need to get rid of the natural log, and the way you do that is to take the exponential function of both sides. When you take the exponential of a natural log, the natural log goes away, and you do the same thing to the right-hand side, and you take the exponential of this function, and you get the exponential of minus t over rc. And then it's just a little bit more algebra to solve for q. So rearranging that, we've brought the 1 over to the other side, and then we can multiply both sides by a negative 1 again to make this q positive. And so we get q over ce is equal to this term. To get q by itself, we multiply both sides by c times e, and that gives us q is equal to ce times 1 minus the exponential function of minus t over rc. Now let's look at this ce term here, because remember, this E is really a voltage. That's the EMF, or the voltage, and so we know from the fundamental capacitor equation that the charge on a capacitor is C times V, or in this case, C times E. So the units here work out. The units of T and RC have to be dimensionless, because that's the argument of the exponential function. You're not allowed to have any units inside the exponential function. And so that tells you that the resistance times the capacitance has to have units of seconds, or units of time. And this has units of Q, which is what we would expect, so the units do work out. A few things that I want to note here. That value, R times C, is known as the time constant of the circuit. So RC is the time constant, and we know that it's going to have units of something like seconds. And also, let's not lose sight of what it is that we actually have here. So this expression, this is the charge on the capacitor as a function of time. This is Q as a function of time, the charge on the capacitor as a function of time. And we can look at some limiting cases of that real quickly. So I've rewritten this a little bit, put the exponential in the normal e to the power form, and notice that we have a minus here. That means that this is 1 over e to the t over rc. So we're going to look at what happens as you change the time, what happens to the q on the capacitor. So the first thing that we can note, if t is equal to 0, that means this is e to the 0 power, and anything to the 0 power is 1. And then you have 1 minus 1, well, that's just 0. So we can note that at t equals to 0, q is equal to 0. And that's what we would expect. When you're charging the capacitor, you flip the switch, there's no charge on the capacitor yet. There hasn't been time for it to move. And so the charge on the capacitor when you first flip the switch, as the capacitor is charging, is 0. But the charge starts to build up, and we can also ask what happens as t gets very, very large. Well, this term, the second term here, that is, as t gets big, this is 1, remember this minus sign means this is 1 over that. And so as t gets big, the exponential function gets bigger, you're dividing by a bigger number, and so basically this term goes to 0 at t equal to infinity then, or as t goes to infinity, q goes to q naught. And that would be the charge on the capacitor equal to CE, which is what we would expect it to be. And so we see that the results are consistent. Finally, on this slide, there's one other piece of information that we can note. If I consider this fundamental capacitor equation again, if I've got Q is equal to CV. If I want to know what V is, I just need to divide Q by C. Everything else will be the same, but we'll lose that C, and I'll get that V is equal to E times that same bracketed function. Remember, the EMF is just a voltage. This guy has no units, so the units work out, and this gives me the voltage across the plates of the capacitor as a function of time. And we can see the behavior would be the same for the voltage. At t equals to 0, there's no voltage across the plates. At t equals to infinity, or as t goes to infinity, we would expect the voltage to approach epsilon. Now, if we look at this function v, we can graph it as well. And we know that at t equals to 0, the voltage is going to be 0. It's going to increase, and it's asymptotically going to approach this value that v is equal to epsilon, the EMF. And that is what the behavior of this function would look like. So it increases to this value asymptotically. Now, we talked about that RC value, the time constant, and you can note that as you go through successive time constants, you see the pattern of behavior, and this will be true for any capacitor. The first time constant that you get, the capacitor will reach 63% of a full charge, or 0.63, the full voltage or the full charge. And after 2 time constants, you're getting very close to the asymptotic value, and basically by the time you reach the 3rd time constant, your capacitor is fully charged and reaching its maximum voltage. Lastly, we want to consider the current. Now, we've looked at the voltage as a function of time and the charge as a function of time. We can also consider the current as a function of time. So we know that current is I, and that's defined as the derivative of charge with respect to time. And so for Q, I can just plug in the expression for charge and take the derivative with respect to time. This first term is a constant, so the derivative of that will go to 0. And we're left with minus e to the minus t over rc. And so we can take that derivative. We'll have this ce, which distributes across. And then we have the derivative of the exponential function is just that function itself. Then you get this minus sign is here in front, but when you take the derivative of this, you'll also get a minus 1 over RC from the chain rule, and that factor is right there. And when you multiply it all and simplify, you get that the current is E over R times e to the minus t over RC. And so we can see that the current behaves differently than the voltage or the charge, in this case of a charging capacitor, because here we get an exponential decay. And so if I look at the values, if t is equal to 0, this whole thing becomes 1, and we're left with E over R, and that would be some maximum value. So at t equals to 0, we would expect E over R to be the value of the current, and then it would exponentially fall off towards 0. And as t goes to infinity, this term goes to 0, similarly as we said in the last slide, because we're dividing by something that's getting bigger and bigger. So this is how the behavior for a charging capacitor works.